I don't know yet. I hope so. Everywhere. Just put me everywhere. I'll be like 5 places at once. Be sweet. There we go. Is that back up? Okay. I can see my slides. You can see my slides. Welcome. Why not? Oh, welcome again. Hold on a second. Let me use my brain. Share.
More. Yeah.
More. Share.
Yes.
This one. Right?
I think you have to
Where's the
share
full
the-
one?
You probably have to share the P first and then go back to here.
No, I think it's like, you should put it PowerPoint and then. Yeah, and you should go full screen.
Full screen here. Hey, did it work?
No.
Somebody smarter than me want to do this? I'm sharing my screen.
You have to start sharing, share the screen first and then choose it.
Share. Let's try this. Does that work? Yeah?
Yeah, it's one word.
Awesome. Okay, welcome. So there's this world of optics that everybody knows about, right? Polishing lenses, refracting light, and then there's the world of diffraction, right? And then there's the world of total internal reflections, and then there's the world of waveguiding through hollow fibers, right? These are all optical systems and principles that at some point I hope you come across. But the one that I'm going to get into today is making effectively a hall of mirrors for light on a chip, right? And if we were able to do that, and I live in the world of sort of possible, but not yet ready to go, then we'd be able to do all sorts of crazy things. So stacking these photonic devices onto electronic devices leads to a whole host of possibilities, one of which I'll talk about right now. So, you know, in many ways, artificial intelligence could make our life better, but it hasn't yet. And one of the reasons I believe it hasn't is because when I do anything with AI, I ship it over to a server owned by, I don't know, let's call it Google. We'll throw them under the bus. And they have stuff that happens on their server, and then it comes back to me on my phone. I don't really like that. That doesn't feel right to me. So, you know, while AI may be cool and help us to identify problems and find things out, you know, bombs or terrorists, whatever it may be, it's not great. I mean, it can recognize vowels. There's a guy who had a computer watch him talk and watch his lips move, and it was able to mimic a zebra finch to the point where his dog attacked his computer. I mean, attacked his computer because it thought it was a bird, right? So he was able to create mimicry with AI, which was special. And it was the first time that artificial intelligence, without any rules whatsoever, was able to figure out what a vowel was. Kind of neat. You know, at the same time, we have AI that's now going into these medical devices where they're trying to figure out cancer on a pathology slide without a doctor having to flag it. And these slides, I mean, each one's like 5 gigabytes. And if you add up all of the amount of information on those slides, it's actually a fair amount of information that's going through a single individual company. And so it's kind of like AI would be great, but there's so much data, we get lost in it and we can't fit it all into the palm of our hand. So you have petabytes of data looking at, you know, different pathology slides. You have petabytes of data when you're observing, right? I don't know, maybe it's more, maybe it's less, but it's a lot. And in the world of healthcare, that's an important thing because you don't want somebody to go rifle through that and find some protected information, right? That's a lot of information to protect. And doing so in the palm of your hand would be easier than shuffling data to a server, shuffling it back and forth and having it transit. So we want to watch out for these, right? Now, a lot of this is like in the healthcare camp, so bear with me because it'll get more, it'll diverge a little later. But if we wanted to put petabytes like into the phone in our hand, it's like thousands of chips, millions of chips. Like when you start to do the math and think about how would you take a wafer, which might have 1,000 chips, and get 1,000 wafers into a phone, right? Like how would you fit all those chips into a phone? Let's just forget about optics for a second. Let's think about using electronics. How could I fit it It would be crazy. I mean, skip these. These are all healthcare stuff, right? Healthcare, 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 healthcare. All right. Most chips today are a thousandth of an inch thick, maybe 10 microns thick. So that gives you, yes, what's up?
Did you open your microphone?
I don't have a microphone, do I? Audio's on. My audio's on. And my computer thinks I'm talking.
Okay.
Yeah,
Um,
we can hear you online.
awesome. So, most chips are like a thousandth of an inch thick. And so you say, okay, I need a million chips. They're 25 microns thick. That's clearly not going to fit in a phone, right? I stack them all up. It's like a meters thick object funneling megawatts. And worse, if I wanted to make all of that, I'd need more people than this country has doing fabrication. It's like untenable. We can't do it. So, you know, holding a lightsaber, right? That's what we would need to put the power of a server in the palm of our hand using electronics today. Something has to give. Our brains don't take megawatts. They're like, in the literature, people say it's 20 watts. That's a big difference, right? So what do our brains do that electronics don't do? How could we do it? And maybe we could somehow, some way take the capability of a human brain or an animal, whatever, a rat, whatever, and interface it to a computer chip. Well, they've done that, right? People have taken voltage clamps and looked at action potentials and said, "Hey, I can see calcium in a microscope." And yeah, those are action potentials. Look, it's pretty, right? But at the end of the day, the action potentials traveling down a neuron is like a bus traveling down the road. What you really want to know is the neurotransmitters, what they're doing, what are they, where are they going, right? And we can't do that yet. So there's some arguments for being able to get a neuron to root onto a device and emit its neurotransmitters and see them with light. Now, interestingly enough, you can cause action potentials with near IR2 light. So like a telescope, we just picked our wavelength, okay? Near IR2 light. What's good with near IR2? What's transparent to near IR2? Silicon is transparent to near IR2, right? What else do we need? We need to be able to stimulate it with light. We need to be able to stimulate a marker with light, and we need that marker to emit. Well, markers now, you can buy them from Sigma Aldrich. They're near IR2 compatible. So we have a neuron will create an action potential with near IR2 light. We have a silicon as a platform to handle that near IR2 light. And we have neurotransmitters that will shine out and emit and fluoresce at near IR2 light if we do the chemistry right.
What's near IR2?
It's like, if I remember right, something like 1,000 to 1,500 nanometers.
Okay. This is
Right,
like a
so
pass
yeah,
band.
it's a band,
Okay.
right? And normally I guess for the fluorophores that are out there, they're like 1064. The neurons will start shooting action potentials at 1,100. It's a thermal process, and 1,400. I'm not sure which is and why, but they've seen it. So it's like, okay, let's build these puzzle pieces together. All right, so this is cool, but the issue then we run into is, well, we still can't use electronics. We still can't use electrodes because hot neurons die and computer chips get hot, right? If you don't cool a chip, your thing will set on fire. And 43 degrees C is not very hot. That's where the neurons will just completely die. So how could we do it? Well, let's just throw out the electrons as much as possible. Let's use photons, right? So in photons, what could we do? Well, we could use a periodic pattern, create a metamaterial lens, and if we could stack layers of that metamaterial lens onto some interposer that had electrodes to an imager or so forth, we could have the photons go through the lens, hit the imager, and have all the computation happening over here where it's hot. And so we'd have a bit of routing, but we could put the photons through a photonic crystal onto an imager. And if those photons were shot through the photonic crystal, hit the neuron, excited an action potential that led to a neurotransmitter that we then dumped back down in the imager, hey, maybe we could close the loop. And so that's the idea of stacking something onto an electro-optic layer and interfacing it with neurons. Now, I'll add one other kind of caveat here. The group that I was working with at Tufts, they have a way to isolate axons from the synapses. And so the idea was to root the synapse right at the point where the light would be stimulating the synaptic vesicles. right, where you wanted it to be. So you'd know it was that neuron sending you those synaptic vesicles at the surface where your focusing was happening, right? And so this is the idea that we were working on. But, you know, we still have to be able to stack membranes. These membranes, they're not a micron thick. They're thinner. They're nanometers thick. They're 150 nanometers thick. And we need to be able to do it in high volume. And we need to be able, so how would you go about manufacturing something where the Z density goes up by 1000x, right? Like today, their layers are 10 microns thick at best. That's what they can handle. If they go thinner than that, it breaks. You don't want to be the guy to tell Bob, your boss, that you broke a $10,000 wafer, right? It's just not a good day if you try and thin it past 10 microns. So nobody tries, right? And to understand how to do it, we have to kind of think about how electronics have gone. I mean, the reality of it is, for a long time, going smaller was easy. And so over year, they called it the semiconductor gravy train, right? Because they kept making the profits they wanted to, and they kept going smaller and smaller and making more profits. But then all of a sudden it got hard, right? And around 2013, going smaller didn't get cheaper. In fact, the cost of the transistors kind of flatlined, which was horrible for big business because they weren't making more money by going smaller in area. And there's a lot of things this that has enabled. It's enabled things like, special neuromorphic computing, or, optical spectroscopy on chip. So there's a lot there that's really cool. But if we want to think about how to pack more in, and we can't make a finer pitch pattern easily, and don't get me started on EUV, I'll go off on a tangent, but it's hard to make it smaller, right? So we have to make more in the Z direction. And if you look at it and you think about how things are made, how you make a diffraction grating to a computer chip, it all follows this step of doing lithography, which is a fundamentally planar process. You shoot light down on a plane and expose photoresist and then do something to it, whether it's etch, grow, like deposit, dope, lift off, a damage, whatever those process steps are, it's planar. And you're trying to go to 3D. So if you try and go to 3D, what you do is you do planar, and then you build stuff up, and you do planar, and then you build stuff up and build stuff up and build stuff up. And that's what they do to make transistors, which, like, a cross section of a transistor is shown on the right there, right? All the way up to the big lead solder bump that they can connect to a printed circuit board. Now, this is, I took that picture from Wikipedia. I'm sure there's other designs and there's other cool stuff out there. But at the end of the day, there's like 10, 15 metal layers on there that make the whole thing way, way thicker than 154 nanometers. And so the industry at large does not need to handle something 154 nanometers thick. If you talk to the guys who do back grinding, Disco is a company, they say the thinnest it'll ever be is 3 microns because of all the metallization, right? But optics, photonics, crystalline photonics, not silicon photonics, but like photonics derived from crystallinity, where you're drilling a hole through a mirror and light is going through that hole because it has nowhere else to go, requires being able to put the waveguides where you want to be able to stack these membranes, because you really can't print it holographically, right? And you can't embed the waveguides you want in just a stack of photoresist because the index of refraction isn't good enough to support a broad spectrum of wavelengths. You really want to do it in silicon. Silicon has an excellent index contrast with air. And so if you're able to put waveguides and devices into a stacked structure of silicon, you could fit a lot of light. And we'll talk about, I did one example later, but we'll get there. So some people, these are the ideas of going to 3D monolithically. Remember, litho, grow, litho, grow, litho, grow, build it up, and so forth, right? And it's complicated. I mean, they've got memory interleaved with computing and these vertical connectors that, by the way, the vias aren't straight lines. They're like cones, because as you etch through the material, it pinches off at a 10-to-1 aspect ratio. So if your layer is 25 microns thick, that means your hole is like 2.5 microns in diameter. And at the end of the day, what that means is that hole consumes a lot of area for transistors. And so there's a lot of problems with monolithically building these things up, but that's what they're trying to do because they need to pack devices in and get their memory closer to their compute and make more powerful processors. So when we go do our crazy stuff with GPUs, it works, right? But ultimately, Lithography is fundamentally a planar process. And if you take a lithographic step and you mix it with all these other processes, at some step in this like multi-layer build, you're going to screw up. And if you screw up at the 1,000th layer, you don't want to tell Bob, your boss, that you like screwed up a really expensive wafer. So if you take lithography and you set it aside, you take stacking and you set it aside, and you look at the good lithography and you look at the bad lithography, and you take your known good dyes and you stack those up, it would work as long as your stacking process is robust, right? So what is it that makes that hard? And one of the things that we thought a lot about was, well, where is the industry going? Why hasn't it really penetrated? And this is old, but the 3D devices, they're a small part. I mean, a handful of $1 billion versus $100 billion of the industry. And I know that this has changed over the last 5 years. This is dated, but at the same time, penetration of 3D devices is stymied by the fact that the vias and the interconnects to these like chip to chip interconnects through solder is the weak point. So when it gets hot, things will move. I was talking with Steve Wallace, who was a program director at Micron, and he told me, when I turn on my stacked chip, the morning it's working fine, but by the afternoon it stops working because stuff moves around. And so electrons are bad. I got Carl McCants, who's like a special advisor to the director of DARPA, to stand in front of the NDIA and tell everybody that photons are like cruise missiles. They dodge most everything, while electrons are like toddlers and run into everything. And that makes all the difference when you're trying to avoid some of these issues, right? So, all right. If we look at it, a transistor today, it's tiny. The gate is tens of atoms wide, but it's sitting on a substrate maybe 100,000 times thicker. Right? So there's plenty of room in that substrate thickness where they could make them thinner. Not necessarily sure they want to, right? There's no good way to get there. AI is going to continue for a long period of time until we can do nanoconstruction at large, until we can do some of these other architectures. It's going to be ship it to the server and the server ships it back. There's no way to put it in the palm of our hand unless we're able to make living devices on this sort of an interface that is doing computations in a much more parallel form than we can make computers do. Right? And so that's the thesis of the work that I left at Tufts. I would say that there's another caveat to that, which is you can't actually make, when we think of our telescopes, right? Those are systems that information is flowing in the direction orthogonal, right? And I know there's like lenses, but it's flowing through the system. It's not flowing across the system. So imaging systems, optical systems, are systems where information, especially as you miniaturize your system, is kind of flowing out of the plane. And that makes them a really great candidate for some of these stacking technologies where you're controlling the structuring and the patterning of things out of the plane. And in some ways you could imagine this like, okay, we all know about the bread size CubeSats, right? But what about the wafer sat? What about the chip sat? What about that? Let's shoot chips to Alpha Centauri because they're so light and we can make solar sails out of them, right? These things, they require swap manufacturing that's vanishing, where things are so light that they don't feel weight anymore. And so being able to handle 150 nanometer thick objects and put them into constructs, however you may want to do it, is a really interesting technology for some of these really, really low swap satellite applications. So the idea of layer upon layer assembly, right? You start with a device wafer, you put it on a carrier, you take that wafer on a carrier, you turn it into a membrane on a carrier by thinning it down somehow. Then you take it, you put it on a receiver, right? You have to handshake from a carrier to receiver because the business is on the front and you have to thin the back. So you have to do this handshaking process. Once you put it on the receiver, you can go and do that as many times as you want with good, as long as your stacking process is good, you could make a 1,000,000 chip stack, right? Once you're done with that, then you go out of assembly into the integration process, bump bond, whatever it is, tie it into the outside world, package it and ship it out. So where do things go wrong? Well, 10 microns, 50 microns, pretty thin. You try and take a 50 micron 12-inch wafer, I think in this case it was 4 inches or 5 inches, but whatever, it breaks, right? When shit breaks, your boss gets mad. Okay, so you try and take a 50 micron wafer off of a 5-inch carrier by rinsing out an adhesive through holes in the backside. The adhesion of the liquid is enough to break it, right? We're talking the adhesion. I mean, this is like 10 millinewtons per meter, for a surface energy for some of these solvents. Like it's small. It's enough to break these wafers. And okay, so let's skip that. Let's go in and let's do what's commercial. Let's go in and let's burn it off, right? Now I've got carbon. I've ablated it. Now I've got carbon films that are left on my wafer, and I've got to get that off. I've got to dunk it in another process. Anytime I interject a process into this is bad, right? So what are we going to do? The problem is adhesion and cohesion. Okay. If you have a device layer super thin on a carrier and you want to get that device layer off that carrier, you have to think a lot about adhesion, because if the cohesion of that device wafer is less than the adhesion at any point, it's going to break. These are things that shatter: silicon, glass, things that break easily. We have a way to do that, right? I'll tell you about it in a second. But if you were able to avoid this root cause, like think about it. You could take a lattice of one thing and put it on a lattice of another and screw with band gaps, right? You could make optical elements that are grid lenses have multi layers of different stuff, right? There's so many things you could do if you had a just generic stacking process. And I hate to think about the scale of everything I'm talking about versus the scale of the stuff that we're concerned about, because it's tiny. Right? This is like in the depths of the integration. This is in the, I fabricated a wafer that's special and I'm going to combine it with another wafer that's special. It's not, I have a 5-meter mirror, right? It's all very small. 3D photonic crystals, tissue scaffolds, metamaterials, these are all things that could benefit from such an assembly process. So it's deeper than just let's make better AI, right? There's all this room down there, as Feynman alluded to, there's all this room, and we've gotten real close to capturing the available room. We can manufacture things that are tens of atoms across, but they're sitting on substrates that are 100,000 atoms thick. And so there's plenty of room to play. There's a lot of innovation that we're missing out on because we can't do it. And I like to show this. This is how would you make a photonic crystal? A photonic crystal is a mirror, right? It's a Bragg mirror, but in 3D. You shoot light at it, it bounces off. You drill a hole in a mirror, light goes through. You put cavities and quantum dots inside of a mirror, or inside of a waveguide, and you can start to do really interesting things like make optical switches on a chip. Not as small as transistors unless you're using X-rays, but small enough to do interesting things. And it's cool. I think Dirk England at MIT has an FPGA that's a silicon photonics FPGA that's 10 to the 5 times less energy per bit than the standard computer, right? I mean, femtojoules per bit, but it's in silicon nitride. It's in silicon nitride. It's in a material. You shoot the light through a material and it gets absorbed and it dissipates. If you drill a hole in a mirror and you send light in, it doesn't. It's a totally different thing. And he's already 5 orders of magnitude. So that megawatts, right? If we were building a photonic computer instead of this, like, let's put neurons on top. If we were building a photonic computer and capacity didn't matter, we could do it. We can make it thinner. We can make it a couple millimeters thick. Right? We just don't have the capacity. And so, I think we should pay people to make 3D photonic crystals. That's my message. If we could make 3D photonic crystals, I imagine we would come up with all sorts of interesting things we could do with it in a space realm, down to a bio realm, down to like a let's dance around the moon realm. I don't know. Just if we could make 3D photonic crystals however we wanted, there's a whole world out there that we don't have access to that we would have access to. 3D photonic crystals have a band gap. Anything in the band gap will be reflected. But if you drill a hole through it, that's how light goes through, right? So you can puncture the band gap in a defined way. You can make light turn 90-degree corners. You can make it wrap around in a circle, and make a resonator, right? You can do your split ring resonators. You can do really, really high finesse cavities where light will just sit there, bounce around. And oh, look, I made a delay line. And for some reason, all those spooky people love those things. And I don't know why. But what I presented, because I opened my mouth when I shouldn't have, was a Uber spectral CubeSat, right? Because I was talking with the director of IARPA and I said, imagine if you could slip 100 nanometer thick computer chip inside a stack and nobody would know it was there. And he said, well, you should come talk to us and let's, have you be a program director, which I'm really glad I'm not doing any of that right now because of the state of things. But I ran through the calculations. So it looks like an 8-inch wafer, you get, roughly speaking, 5 meters ground surface distance, right? You could have like quadrillion waveguides on that 8-inch wafer. And by the way, there's technologies to pattern an entire wafer. There's Cerebras, which is like the world's biggest computer chip. Imagine 2,000 bands, right? In something that's less than 2 millimeters thick and 72 grams, right? An 18% band gap that we could make with these photonic structures. We're talking like hyperspectral is like 10 nanometer bands. This is like 1 nanometer bands, right? We're pushing it where you can start to really almost see isotopes. Right? If you could make 1 nanometer, does anybody know what a hyperspectral imager does? Raise your hand if you don't. All right. So hyperspectral imager, right? You take in light, you divvy it up into a whole bunch of different bands. You want to see CO2? You want to see why that submarine was carrying like drugs? You use hyperspectral imagers. That's what they do, right? And so you divvy up the bands. Now you've got a picture, and in this direction you've got a bunch of information about light in different bands, and you can use those different bands of light to assess whether that tarp covered submarine is carrying cocaine or not. And that was the example they gave me when I went and talked to the airport. So yeah, I'm not entirely sure what I don't know. It makes sense. I mean, but it's a lot of data, right? That's the downside. And what I was looking at was, well, what if you had finer bands? What if you could make it smaller? What if you could make a satellite? And so that was the practical example that could be a fun, but problem was that they already had a new hyperspectral program being kicked off when I pitched this. And so it got not really a warm reception because they'd already signed the dotted line. And that was my IARPA experience. So anyways, if I go much further, I'm going to kick myself because it's lunchtime. I could go 50 more slides, but I think I'll save you that. At the end of the day, right, what I want to leave you with is we have not conquered the nanoscale yet. Computer chips are great. Lithography is great. Extreme ultraviolet is cool. Like, not great, but cool. But at the end of the day, when we're making devices and we're putting things on substrates that are, many orders of magnitude thicker, there's a lot of room for innovation. And some of that innovation bleeds over into space. I'm not exactly sure where that happens, but I'd be more than happy to entertain the conversations and figure it out. Anyways, thank you much. I hope I strung it together. I haven't looked at these slides in a couple of years. Questions? Thoughts?
Question for you though, costs have come a lot for the expected things to do. I know that can be a lot of limitations for that. Especially with kind of like what you're proposing in a way, and like dealing with the byproducts as well, or anything like that for them kind of process.
Mm-hmm.
How does that look in comparison to like how it is?
So it's about 40% of what it costs to make a transistor. Because when you do transistors, there's all these things involved. Metallization steps are expensive when you're taking, so if you make one of these things right here, where it's just layers of holes, right? You take silicon on insulator wafer, right? You put an anti-reflection coating, you throw down an evaporation step to put an inner layer, and you put some photoresist on top. And you pattern the photoresist using interference lithography, which if anybody wants to make gratings, please talk to me. Pattern it with interference lithography, right? Now you've got a grid pattern. You've got this holy pattern, and there's a lot of details there, but you can make it. And then you take that, which is a negative photoresist, it's a latent image, and you draw your waveguide, right? So now you've effectively created a device. And then you develop it, you reactive ion etch it into the silicon, and you're more or less done with your planar fab. There's no deposition, there's no metallization, right? There's no Damascene process, there's no CMP, right? When you put it onto a carrier and you back grind away the silicon, that's a water process. There's no alumina, it's all diamond ground, right? Then you have one other step, which is like a post wet etch. You throw it in some KOH. KOH is relatively cheap, not the worst. You don't need to use TMAH. The sufficient, you can grind down to like 10 microns, and you can have about a micron of glass, and the selectivity is like 1,000 to 1. So when you hit the end of that glass, there's the end of the silicon and stop on the glass, you have plenty of time to figure that out before you would destroy your device. And then it's an HF step to get rid of the glass, and you're left with this pristine membrane sitting on a carrier on a glue that you can remove. And the removal of that glue that I alluded to, I don't know, I must have skipped it. You just vaporize it. That's something we did at MIT, and you just vaporize it, and it's gone, and the things detach and they don't break. So it's easy, much easier than they've made it to be. You don't have to use wax, you don't have to use special polymers. You just vaporize the glue and things fall apart.
Special. Or like a special polymer in a way.
Oh, no, it was much simpler than that. Significantly simpler than that. Cheaper too. Yeah, there's an interesting paper, right? So I can skirt the question. In the very beginning, when they were using PMMA to do lithography, right? They talked about it, they'd shine light on it, and the PMMA would outgas and it would vaporize. And they didn't really think about it. They said, well, we just shine light on it and we develop it, right? But in the beginning days, there was no such thing as electronic grade materials. So they were using PMMA that was coming out of a paint can, okay? And the PMMA wasn't characterized. They didn't know, was it 950 kilodalton or was it 3 kilodalton, right? So that's the essence of it, is if you use a big, like long chain material, then you're talking like 10 to the minus 18 to 10 to the minus 12 to get it to vaporize. It's hard, right? You got to punch that with so much energy that you're going to destroy it before it vaporizes. Those things are expensive. The things that you don't have to punch hard are cheap. So that's the advantage. So there's a lot of cost savings, and the process to make, on a 4-inch wafer, I could easily make 36 layers, without too much difficulty, like, just doing that process that I described. Like, you draw a line, but you also can mask it. So you get islands, and then you take those islands and move from there. Like, the process is good. During my PhD, we would float the membranes off. Where did I go? We'd like pattern them, and then we'd put them in, we'd float them, we'd pick them up, we'd stack them. And we kind of came to the conclusion that there's a lot of ways to manipulate floating membranes, but at the end of the day, if they're floating, then you've already lost because you can't align them to anything else. And so we came up with this other thing that wasn't water anymore. It was just one of these vaporizable compounds, and that solved the problem. So significantly cheaper. Now, the quantum dots part of it is tricky because, like, Hewlett Packard has this thing that's doing like quantum computing using nitrogen vacancy centers in diamond. And they have these diamond materials where there's impurities, like Lizzie's ring is blue because there's boron in it, right? Yellow diamond has nitrogen vacancies in it. The color of diamond has everything to do with the impurities that are in there. And they can take that impurity and they shoot light at it, and it resonates. And if they shoot 2 wavelengths of light, it resonates again. As long as those wavelengths are the right wavelengths, they'll both come out. But if they shoot the second wavelength in and not the first, nothing comes out. Problem is they can't put the nitrogen vacancies where they want. And this was like 2009, and they still don't have a computer made out of it, right? So it just goes to show you that putting a quantum dot where you want is difficult. And so if you wanted to make a photonic computer and you had a layer that had quantum dots in it, you might be able to make that the hard layer and draw your lines to that and make everything else the easy layers. But until you can like put the quantum dots, and there's other processes where they'll de-wet like 2,6 materials inside a stack of others to create the quantum dots. And it's the same process. It's chaotic. They have no idea where they are. So they have to pattern the quantum dots and then subsequently get to them with a waveguide. So that is a challenge still. Who wants to stack membranes? Okay, besides me. Anyways, that's it, guys. Let's eat. You don't have to sit here. Has anybody like looked at a diffraction grating and just been like, that's a great rainbow? Like, has that visceral response struck any of you? When you can make it, when you can pattern it, when you can shoot light at photoresist and create a rainbow, it's like, it's really kind of a special feeling. I don't know. It's just, ever since I did interference lithography once, I miss it. So interference lithography, right? There's a cart before the horse. I went too far. See this. No, this. No, this. All right, interference lithography. Right? There's a Lloyd's mirror. Right? You have a mirror, you shoot light, the light bounces off the mirror, folds, and creates a grating, right? That one's great because the optical path length difference is rather small, but it only patterns a stripe on a substrate. You can make like an inch band of diffraction grating on a substrate. If you want to make the whole wafer, you have to use something called like a Mach-Zehnder or a scanning beam system. And if you try and overlay multiple patterns, right, because you're using these systems that drift, you'll have errors. Like 3 days, I had 8 milliradians of error between two patterns. And so it's really difficult to overlay a pattern of rods and a pattern of holes. But if you want to get the best band gap, you need to have rods and holes. So we came up with a system called coherent diffraction lithography, which is now in my office, not here, but at home, where we could take a mask that was patterned with a phase mask and hold it parallel to a substrate and replicate the phase mask pattern in the substrate by putting it at the Talbot plane. But you need to be able to hold the mask relative to the substrate at a 2-micron gap to capture the first Talbot plane. And so we're using a interferometric alignment where you can move a grating over another grating and fringes move. And if you register those fringes to a fiducial, you can get 6-axis control of two substrates. And so there's a lot of fabrication knowledge here that comes down to you could use the same interferometric metrology to do stacking. So the ability to pattern and the ability to stack are kind of the same tool. But the debonding step requires a special environment that we just didn't have during my PhD. And so bye-bye. Do it again later. You guys, I'll keep talking unless you stop me. Like seriously, Lizzie knows this.
Stop.
Yeah,
Stop.
please.
I think everyone is waiting for you.
Oh, I have to eat. No, I have my own lunch, guys. Please don't wait for me. No, please.
Sit down snacks.
That's okay. That's okay. I eat peanut butter and jelly. I had a video that was really cool.
No, he's like a
Annie.
fabrication.
You're not gonna eat any of
Like,
No, it's okay. I packed lunch.
I feel like he would have really.
I always love that video. Oh. That's easy.